No? Okay. Well, welcome for the presentation I want to do on a topic that I felt could very much fit to the discussion that we have been having during the last couple of days, namely how to obtain a non-Fermi liquid phase in a system not at a critical point, but in an extended region of phase diagram. And it is work that was done together with these three gentlemen from the Weizmann Institute. Two of them, Evyatar Tulipman and Eris Berg, are here in the room, and Noga Bashan is not, but have been involved in these discussions up to the last moments. Both of these young men, I should say, have put an enormous effort into developing this the theory, and I've been enjoying this collaboration in a way that is very much impressive to me. The talk will be, to summarize it, discuss fermions. They will talk to random two-level systems, and we will discuss precisely what we mean by this, and we want to solve this problem. It's a hard problem to solve, and we want to solve it with the philosophy that we have been using during the last number of years in Yukawa SYK-type systems and large N systems that allow for rigorous solutions. And what we then find is that we have, over an extended region in parameter space, non-Fermi liquid behavior with an exponent that can vary continuously as function of dimensionless coupling constants and parameters that characterize the distribution of these two-level systems. They will also then be reflected in, for example, resistivity data and so forth. And you can then imagine a scenario where you start as a Fermi liquid, you change adiabatically a parameter, you enter a marginal Fermi liquid state, you change parameters further, you enter a non-Fermi liquid state, you change it further, and you actually recover to go back to a different Fermi liquid state. So this is essentially what we want to talk about. This is what we know and very much love as a root cause for critical behavior, and hence for example, non-quasiparticle physics, which is the theme of this conference, of this workshop. What we want to therefore discuss is whether this is possible, how you can get it in a controlled fashion, what does it mean, and what is the underlying physics of such a scenario. There are some indications that this is not complete nonsensical. There are these older resistivity data by Nigel Hussey that see a linear temperature dependence in an extended regime of parameters. There are these data that have been shown multiple times during this meeting now from Dan Dessau and collaborators, where you have a self-energy extracted from ARPIS, and the self-energy seems to be governed by an exponent, and this exponent is a quantity that varies continuously as function of, for example, charge carrier concentration in the system. There are other reports. We have seen this in Eric's talk yesterday about some indications for these power laws varying in optical spectra, and even going beyond the Coop rates. There are works here from the Yefetov group that the resistivity behavior being, for example, linear over an extended regime, here in this case of fillings, or of the Cornell group in the tungsten diselenide, where you also have regimes rather than individual and isolated points that seem to show unconventional or critical behavior of some sort or another. The chances that the theory that I will be presenting explains at least.
You don't say anything critical in that resistivity versus temperature law.
In this resistivity versus temperature, yeah, this is, so what you want to look at is here.
Yeah, I spent a lot of time looking at it. I don't say anything critical.
Well,
what is critical there? Can you tell me? I'm just trying to understand what you're saying.
The statement is.
I wrote 2 papers on that. There is no criticality.
There is a temperature dependence of the resistivity that at these low temperatures is an indication that there's some scattering mechanism.
Yeah, it's an indication of the screening is very strongly temperature dependent.
I mean, maybe can I have copies here? The statement is simply that there's an extended regime over which the resistivity is linear. That's all these things.
Yeah.
Statement is very strongly temporally dependent. Completely accepted.
Okay.
Yes.
Completely accept that statement.
Good. This is my rotten brain. This is, of course, this is Abai Pasupasi in Corridin, and you're absolutely right, and I appreciate the comment. Good. So what is the system we wish to look at are fermions, and they seem to be, and we are assuming that they are living on top of some sort of a charged glass. There are multiple origins and interpretations. You can have, just to have one, you could imagine that you have, and this is something we have been thinking about way too many years ago, when you have, for example, phase separation that is frustrated by Coulomb interaction, then you can generate these charge pattern that will, even after a long time, only moderately change. They will freeze. These are results of mean field calculations. And you can even conceive these states to occur if you don't have quench disorder, or if you only have infinitesimal quench disorder. This is a result of frustrated systems. So let's take this as our classical starting point, and then ask the question, what would fluctuations and quantum fluctuations do? And this is, of course, in structural glasses, a much discussed topic. Anderson, Hoppering, Varma, Phillips told us how to think about this problem. You have local regions characterized by, if you wish, so an Ising variable, two-level variable. These typical asymmetries of the field, they are distributed with a distribution function. The good reason that the eigenvalues of these problems have a distribution function that is flat. If you use this, solve the statistical mechanics, average over the field, you get a lead capacity that's linear, and that's a classic result of low temperature excitations of glasses. So these two-level systems are naturally occurring when you go from one of the local metastable states to another local metastable states in such a system. In an electronic system, we can imagine this, for example, like just different arrangements of electronic states. Often, and in this self-generated picture, you need to think about it that this is a collective intermediate scale behavior. It's not something that necessarily occurs on atomic scales. So the way we think about it is that we have some coarse graining going on, where we have a local region where you have, for example, M two-level configurations, and you have n electronic states. And of course, we wish to take n and m large, because then we can control the situation. And we look at such a blob and connect them and build a lattice out of this, and therefore have local degrees of freedom that are for these Ising variables coupled, and electrons that propagate in the system and coupled to these local degrees of freedom. So the model is the one that I'm giving you here. We have electrons with kinetic energy. The label I are these internal degrees of freedom of these little mesoscopic blocks that I have indicated. There are two-level variables. They're coupled to a field that's random and distributed. There's an interaction between the two, in addition to a disorder term that I won't discuss a whole lot today. There's a coupling constant that couples the two-level systems to the electron excitations of the system. These two are distributed quantities. They can, in principle, look in all kinds of different directions, given this two-level system, with the one exception that the field should, if this is a charge class, in respects time reverse symmetry, has only two components. Very well. So, G is all component. It could, in principle, couple to a local current in the system. So by time reversal symmetry, if G would have to be an imaginary quantity that couples to, it would then produce a local current in the system.
Two-level system is not a dynamical variable.
The two-level system is well, if this is a spin operator.
Okay, so you're the basic equation of motion also.
Yes. Yeah. So. Good. So we have a distribution function for this coupling constant. We have distribution functions for these spins. And this is, in principle, a complicated problem. And there's one regime where you can immediately see the solution. If these two vectors that couple to these variables all point in the same direction, or at each point in the same direction, problem is completely trivial, because you can then diagonalize the spin in that basis. So they are classical objects, and there's not a whole lot interesting happening in the system. It becomes more interesting in a more generic situation when they are not diagonalizable at each point in the same basis, and then there's will be quantum fluctuation. For example, the two-level system, even its own eigenstate, will then couple, and you have the electron-assisted tunneling in the system, and so forth.
Joerg, do I understand that the interaction is the electron excite the two-level system, or does it scatter off the two-level system elastically in the two-level system being in one of two states?
So the picture I have is that you have configurations, for example, of charge densities, and they could tunnel between different configurations, and the electrons couple to those. So probably these two-level systems are somehow generated out of electronic degrees of freedom, but of course that's not what this model here says.
My question was, the electron is scattering off elastically off of the two-level system that is different.
Well, this is a quantum mechanical degree of freedom, so it can also dynamically scatter off it. Yeah.
Okay. Yeah. So it can excite the two-level system.
Of course, yeah, it can excite, yes. So we will look at the moment in a special case where we say go to the eigenbasis of this two-level system or point it in a specific direction and have these random couplings going in some orthogonal direction. Noga and Eviatar have spent more time than they maybe wanted to look at all other cases. And unless you go into a trivial system where you can diagonalize every state locally because it's an eigenbasis, so these two vectors are parallel, unless you're in this situation, everything seems to be flowing to a regime that is governed by, for example, this behavior where you have fluctuations, so tunneling induced by the propagation of electrons that are governed by their own two-level distribution function. The distribution function itself, we are looking at two cases. One is when the distribution function is flat, or when it's linear. There are good reasons for both of them, depending on which basis you're looking, what the correlation functions of the coupling constant and are so forth, and I can discuss this later as I want to. We have a pretty good understanding of what happens for generic distribution functions in the system. So, if you're a little bit familiar with the Yukawa-SYK logic, you see there are lots of similarities in the spirit of all of this. What we do is that the bosons that Subir has been discussing are essentially replaced by spin variables. So this was clearly motivating us and is in its spirit what led to this, but there are also distinctions. As we will see, I mean, one is obvious, these are spin variables or two-level variables, they don't obey a Wick theorem. You need to work harder. This implies, and as we will see, that the description of the problem is no longer in a well-defined way of a Migdal-Eliashberg variety. And what it implies also is that the criticality we find then is not limited to any space dimension. Maybe it has to be larger than one, but otherwise it is, would even in 16 dimensions be giving us these critical behavior that I want to.
So are you saying D is the spatial dimension?
Spatial dimension, yes.
So 0 plus 1D is
1 plus 1 would be not something I want to address.
0 plus 1.
But let's start with 2 dimensions, then I feel comfortable. 2 space dimensions. So you do the usual formalism that I really don't have the time to get into to perform these large N calculations in the spirit of the Yukawa-SYK theory. What you find is something that very much for the fermions, which very much looks like Migdal-Eliashberg formalism. So what I've done here is that I said we have coupling constants that we average over what we do this for a distribution that is fixed for the level crossings. So we get a self-energy, we get a Green's function, and so forth. It looks different for the two-level systems. Here we have a correlation function that enters our self-energy calculations, that are our spin correlations. They are governed by something that looks like self-energy. It's a usual one-loop diagram, but you don't obtain this correlation function from a Dyson equation. There's one equation missing in the usual game, and that's why you have to solve this problem. Spins exposed to this dynamical, to the time-dependent field and their distribution function, but this is, of course, a problem that we know very well. That's the spin boson problem. Something that has captivated the interest of many, many also in the room, where we have to solve the dynamics of a spin in a bath. And the bath is not, of course, the bosons here are fermions for that matter, but of course it doesn't matter for the analysis. So we have here a bath degree of freedom and we have spin degrees of freedom. This system is still not translation invariant because I haven't averaged over the two-level splittings.
Your quick question. And the fact that fermions have dispersion doesn't matter here, or it does?
Oh, it does matter, of course. They have dispersion.
So you really have to solve with full fermionic dispersion. And in terms of scales, is Fermi energy the largest
Fermi energy is the largest scale.
Mm-hmm.
Yeah, I think I had it, but it was too quick. The distribution function of two-level systems has a cutoff. This cutoff is much smaller than the Fermi energy to do this type of calculation.
I have a quick question. Why do you have non-local components for the polarization operator? Pi? No, the last line. So,
last line.
Yeah.
That's local, perfectly local, RR.
But fermions are non-local. They can hop.
Fermions are non-local. This
Right.
is, I need to invert this object here. Yeah.
Right, but what about GRR prime? Does that give rise to a dynamical, like a kinetic energy for bosons?
A GRR prime can be calculated if you really want to, but you don't need to know it to calculate the Bars function of this two-level system.
Once you average it with
Yeah.
the copper coupling is spatially random.
Of course.
That's why the pi is local.
Yeah. This is an honest random. It's not an infinitely correlated coupling, but this is a random coupling that is uncorrelated at different sites. Okay. Yes. It has. Of course. Yes. So now this is the problem is still quite non-trivial, but the idea is that in our little blob that we imagine here, where we have these large M degrees of freedom that give us different two-level systems, the picture that we have is that this is self-averaging in the state. So basically what we need, this problem is clearly not translation invariant for a given configuration. But we don't need to know the quantities that are not translation invariant. We only need to know quantities that are actually averaged over the internal flavor degrees of freedom. And this self-averages the system and restores translation invariance in a well-defined way, so that we can then say that our correlation function is translation invariant after this procedure. This is a large N implication, and then can solve the problem, the fermionic problem, with a momentum-independent self-energy, and gets this Bars function and find that it's actually an ohmic Bars that we have to solve. Our two-level system is governed by an ohmic Bars. And then we're almost done. We need to solve the two-level, the spin boson problem for each site. We have to do this for a given field. We take the solution, we average over the field, and then we can determine the self-energy from a one-loop diagram. Good. The solution of a spin boson problem is a classic one. You can look into papers that were written before many of the members in the audience were even born. The idea is that you have a coupling constant in dimensionless units, and that you have this two-level splitting field in dimensionless units. They are undergoing Kostelet-Saul's phase RG equations. You find that what happens is that the distribution function of this two-level system fields that we have to average over in the end of the day gets strongly renormalized in a well-defined way, and we've all, or many of us, have seen these equations. And the second step that's very important is it's this renormalized field that you can calculate from this flow equation that governs the dynamics of these local spins. So when I want to average over them, I'm much better off to know the distribution function of the renormalized field rather than of the bare field that I can assume to be rather simple and trivially looking. Here are examples. Suppose we have a distribution function that even has no support at lowest energies. As function of the coupling constant, it will then renormalize at small coupling constant will look like the bare one. Increasing the coupling constant following these flow equations, you will even get support at low energies. You get a diverging distribution function or even a delta function depending where you are, because depending whether you're flowing upwards or downwards, becoming static or dynamic. So therefore you get a strongly renormalized distribution function of these local fields. But those are the ones that govern the dynamics of the spin degrees of freedom of these two-level systems. And if you then average over them with your now known distribution function subject to this renormalization, you find power law behavior for the spin dynamics with an exponent that governs, that depends on the distribution function, here characterized by an exponent, and governed by the coupling constant as a consequence of this RG procedure that we've just been discussing. So what you see is that you get a critical two-level system dynamics, and the next step is straightforward. You then calculate the self-energy for the specific problem with momentum-independent self-energies and integrating over an energy dispersion with a large Fermi energy. We know exactly what the answer is. You get an exponent gamma. The exponent gamma here then governs us the non-Fermi liquid behavior of these fermions, and we can look at it for typical behavior depending on distribution functions. We find either situations where we start from a marginal Fermi liquid and get into a non-Fermi liquid until these two-level systems freeze, act as impurity scatterers, and then you would recover a Fermi liquid state again. Or if you're more conservative and you have a distribution function that has no supported low energies, then you start from a Fermi liquid, but at some intermediate coupling constant, you go into a marginal Fermi liquid state, you go to a non-Fermi liquid state, and then eventually you can freeze again. S. Oh, these are static impurities. Yes. So this is how you would construct a phase diagram, because this non-Fermi liquid behavior is of course only limited to whatever is the renormalized energy scale for the distribution function. And so you would have this is for a specific realization here. Our Fermi liquid would extend over a certain temperature regime. That temperature regime would become smaller, but always be finite, and eventually you would have a low temperature state that has frozen impurities, has an increased elastic scattering, but still have an excited state that you can scatter off inelastically. This is basically Peter's question from before. It will not surprise you get a resistivity that's governed by the same exponent, because everything here is momentum independent. So we get power law behavior for the exponent. We don't get always a linear resistivity, but we get a resistivity with a power law that would change as function of parameters that you wish to study. So one of the statements we had been discussing is maybe when you constantly have an AT plus BT squared type of behavior, it might be equally interesting to try to understand this in terms of a varying exponent rather than having two quadratic and linear terms that have varying coefficients. This result here is actually, in one limit at least, was obtained in the late 70s already, where the exchange of two-level system was looked at, and for a given distribution function here, you get this exponent, and you got a linear temperature dependence of the resistivity. What was missed by this analysis was, of course, that you have a varying exponent and a critical regime and a critical phase in the system. I'm out of time? Completely out of time? Good. So there's an optical conductivity data that is non-monotonic, because you can also dipole excite these two-level systems if you wish so. There's a heat capacity behavior that looks like what you would expect, even though to get there is hard work. And I can summarize. I told many of the things already. We have electrons that are exposed to a two-level system. The electrons form an ohmic bars, gives rise to a rich behavior where we have critical phases. And this is something that we get because the logic of Migdal-Eliashberg, as we know it in many of these Yukawa SYK stories, doesn't apply because the problem doesn't allow it. To use it, we have to do a little bit different of calculations. We find something interesting in the physical observables. We looked that everything is rather generic, even though the case I presented to you is a special case. We can even ask the question whether this gives rise to superconductivity. It would be S-wave superconductivity. And I can tell you what you get. You get no temperature, zero transition temperature here, no transition temperature here, and a transition temperature that's larger in the middle. So there will have to be some non-monotonic dependence of the superconducting transition temperature induced, for example, by the exchange of two-level systems. Thanks so much for your attention.
Raphael? Joerg, I have two questions. One is kind of trivial. I didn't get in the end, if alpha is larger than 1,
yeah,
like in the first example, then you get gamma negative.
No, you can't. This is only applicable as long for alpha smaller than 1 as when
okay.
This is basically, this is where the BKT flow reverses and you freeze at least a certain subset of all your two-level systems.
And my other question is, can you think of a realization where you're thinking in terms of charge order, but can I think one where I have, for example, local dxz dyz orbitals then
Yeah.
your age X and age Z are
Yes.
random strain, B1G,
Okay.
B2G.
Yeah, you can exactly think like this. Very good idea.
Because that could
Yes.
be for the nematic glasses.
Yeah, we
and
just
so.
need, yeah, it's a very good point.
Can I ask? It seems a crucial assumption responsible for this critical phase is that your P of H has support all the way down to 0H, right?
I can have a problem where one problem I solved has no support at H equals 0, it just starts linear. If it has a gap, we have a problem.
Okay.
Yeah.
So if there's a gap, then
Then
what happens if there's a gap in P of H?
Well, then you don't get a critical phase, right? Then you get a
Okay.
Fermi-liquid phase.
You get a Fermi-liquid.
Yeah.
All right. Thank you.
So, Joerg, great stuff. One of the hallmarks of two-level systems is that they also, besides having a broad distribution of splittings, they have a broad distribution of relaxation times.
Right.
And so would one expect glassiness in a situation like this? Long, slow, logarithmic relaxations, weird aging effects if this sort of thing was going on?
I would expect that, yes. But it's already built in the philosophy of the outset, but I also would expect it to result here, yes.
More questions?
Yeah. Two quick questions. One is sort of philosophical. You put it non-Migdal-Eliashberg description.
Yes.
But you still integrate fermions over dispersion. This is how you get integral from 0 to omega. So in this respect, fermions are still faster than any of your bosons.
Fermions are the fastest one.
Then why not to call it Eliashberg? Just by
Oh, well,
definition.
further, you wouldn't complain, but it is not, the bosonic problem is not in the variety of what you would get out of a Migdal-Eliashberg theory.
More serious question.
Yes.
How to connect this, or is there any way to connect this to original Yukawa SYK, in which Fermi energy is the smallest energy scale, not the largest one?
No, it's a different problem.
Sorry?
Well, I mean, the way we set up and think about the manipulations, yes, but the physical problem is a different one.
Right. But I'm wondering, what will happen if you just neglect fermionic dispersion within this problem and just consider dispersionless fermions?
Then you have strong...
Can I answer that? Sure.
Sure.
Sorry. There's no,
Take microphone.
overall philosophy is certainly similar. I think one difference is they have two-level system. We had a Gaussian field.
Yes.
So this means like there's a 5 to the 4th term in the
Yukawa SYK model, which we pretty much ignored. Whereas here is crucial, the 5 to the 4th term. That's what gives them two-level system.
Right.
And secondly, I think they have distribution of H. That's sort of like a distribution of random mass for the Yukawa SYK. And we generally assume the random mass could be also gauged away into the random coupling.
Yeah.
So they're cousins, but they're looking at rather different limits.
Right. But
And if I may add just one
exactly
formal...
the same model.
Yeah.
You can...
If you can't integrate over fermions, you have a feedback of the fermionic self-energy on the bars that I would not expect any longer to be ohmic. So this will change the philosophy quite dramatically.
A little naive question. So we have a bunch of two-level systems which are coupled, but not with a bosonic mode, but with fermions. But can we still anticipate some sort of decay superradiance physics or some analogs of this when you essentially have those two-level systems acting in sync to emit into your fermionic system?
I wouldn't expect superradiance, but just because this is a very strongly incoherent system. But maybe that's above my pay grade.
I think the superradiant state would be the spin glass. If they became a spin
Right.
glass, that's when they'd be
Yeah.
Okay. Thanks.
Joerg, concerning the specific heat,
Yes.
you have both spin degrees of freedom and
Yes.
then fermionic degrees of freedom.
Yes.
Is it possible does it make sense, first of all, to identify the singular specific heat? Where does it come
Absolutely, it's a very good question. So it comes from the dynamics of the two-level systems.
from? Okay, so it's a bosonic.
Yes,
in quotes.
it's a bosonic contribution.
Okay, maybe last question, and then we should.
Yeah, thanks. I have a question about self-averaging in the system.
Yes.
So you mentioned that the system becomes self-averaging the large n and large
Yes.
m limit. But at least within the Yukawa SYK framework, the self-averaging property begins to break down once you go to higher order in the 1/n correction.
Yes.
So I was wondering if you have thought about these.
Yes, we have. We thought about it. There will be an energy scale that goes with 1/m to an exponent that is given by the spin boson problem, and below this energy scale, all of this will not work.
I see.
At finite m.
That exponent is also varying in the
Correct.
interface. I see. Thank you.
Okay, let's move to the next.
Daria?